What on earth is a Tesla reactor? Other power plants in Red Alert 2 have a pretty clear giveaway as to how it generates power. The nuclear reactor seems to be a nuclear reactor, as the name strongly implies. The Allied power plant has 3 chimneys and something glowing in the center, probably a traditional fossil fuel combustion power station. Boring! The power plant that sparked my interest was the Tesla reactor. There are a lot of things about it that appear strange right away. Why do we see electric arcs shooting out from it? You wouldn't want power losses like that in a power plant. Why does it have pipes going everywhere? It doesn't exactly look like a fossil fuel furnace. And what does the name even mean? What makes this a reactor and how does it relate to Tesla? Let's start with the name. It is supposedly a reactor, a term that is usually synonymous with nuclear reactor when it comes to power plants. But it doesn't look anything like a nuclear reactor, and it doesn't leave the dangerous waste when destroyed like the actual nuclear reactor does. But it could be a chemical reactor, which is essentially just a vessel in which a chemical reaction takes place. It could make sense for a power plant as there are countless chemical reactions that releases energy, but it doesn't really narrow it down all that much. Okay, let's move on to the electric arcing we see during operation. There is no obvious reason why you would want to handle energy transfer in such an inefficient way, wasting energy heating up the air around the power plant, unless it's some kind of overload protection. Using high voltage protective air gaps is a well-established way to protect against overvoltage, where the outside equipment is constantly subject to charged dust particles, that over time can build up a significant voltage potential if not addressed. Once the voltage reaches a certain threshold, it will arc through the air to a ground terminal. This will create a plasma arc through which current can flow, discharging the equipment, similar to what we might be seeing on the Tesla reactor on a larger scale. Now, using an overvoltage limiter as the main overpower protection seems a bit strange. For example, in a nuclear power plant you have thermal protection that slows down the nuclear reaction before it gets out of hand. And you have overpressure protection in case the pressure of the steam created by the thermal output of the nuclear reaction gets too high. You don't let the power surge reach the generators, because they will catch fire if they are operated beyond their limits. And that goes for all power station generators. So again, using high voltage protection air gaps as the primary power limiter makes no sense, unless there are no generators. What if electricity is the primary power output? Then you don't have as many options, so overvoltage protection could be the only viable alternative. So we're looking for a chemical reaction that produces electricity. Let's go back in time and see what we have.
What is that? Who is there?
Building in progress. Unit ready.
Waiting
Construction
order.
complete.
Affirmative.
In the beginning, Alessandro Volta invented the Voltaic Pile, a pile of alternating zinc and copper plates separated with an electrolyte fluid, salt water in this case. As the zinc oxidizes, it releases 2 electrons, which are then accepted by the hydrogen ions in the electrolyte, creating a voltage difference between the zinc plate and the electrolyte. The copper plates make sure that this process only occurs in one direction, making sure that the current needs to flow through an external circuit to neutralize the charge inequalities. Several of these zinc-copper plate pairs can be stacked on top of each other to increase the voltage. Now this makes for a decent battery, but once it runs out you're left with an oxidized pile of useless rust. So it's not very well suited for continuous energy production.
Stand by, comrade, while we attempt another time shift.
Let's jump forward a couple of decades to where William Robert Grove discovers that you can use gas instead of metal discs, with similar results. A gas voltaic battery, as he called it, or as we know it today, a fuel cell. Now, as you might have heard, this is not some old relic technology, this is the technology that will supposedly power the future. One significant improvement over the Voltaic Pile is that the fuel can be continuously replaced, which means that it's not just a battery, it's a power generator. The fuel cell uses oxygen and hydrogen as fuel. Hydrogen is oxidized, resulting in hydrogen ions and free electrons, which creates a potential difference of barely 1 volt. The electrons can travel between the anode and cathode through an external circuit powering it, and the resulting hydrogen ions passes through the electrolyte and recombines with the electron and oxygen to produce water as the main waste product. The fuel cell has been optimized over the years and have been used by NASA on space missions since the mid-60s, for example. But it hasn't really taken off among the general public. It might be due to the fact that even though the fuel cell operation is very environmentally friendly with water as the main waste product, there is still no clean viable way of producing hydrogen. But maybe that's about to change. So is the sphere in the Tesla reactor a fuel cell? Well, a single fuel cell doesn't generate nearly enough voltage to create the arcs we're seeing, but just like the Voltaic Pile, fuel cells can be connected in series to increase the voltage, resulting in a fuel cell stack as it's called. And if we look at the Tesla reactor as it is being built, it looks like the sphere is growing, which might actually be layers of fuel cells we see under construction, which means that it is essentially a jawbreaker. In the center we have a hydrogen chamber, then the anode, electrolyte, cathode, the oxygen chamber, and finally a separator, and then it repeats. So is this a valid theory? Let's recap. Does it explain why it's called a reactor? Yes, it's a chemical reactor. Does it explain all the pipes going everywhere? Yes, for the supply of hydrogen and oxygen, and waste management. Is the spark gap over voltage protection a feasible way of handling power surges? Yeah, it's theoretically possible. Would this be a terrible design for a power plant? Yes. Yes, it would. To reach a high enough voltage to create the arcs we're seeing, you would need to have many thousands of these fuel cells, which would be ridiculously complicated to build. And the output current would be limited to the innermost fuel cell as it has a much smaller surface area than the outermost ones. And the fact that it's arcing all the time would indicate that it is really badly calibrated, as fuel cells in general are very reliable. So I could end here claiming that it's just a terribly inefficient design. But I don't believe that. And we have yet to figure out why it bears Tesla's name. At this point I was struggling to piece it all together, until I found this article that explains everything.
Building infiltrated, technology stolen.
It's about production of green hydrogen, and it shows how it's theoretically possible to produce hydrogen from water and ethanol, and you know Russians know their ethanol. However, this is not easy to achieve, as this combination of molecules can react to form a bunch of unwanted stuff as well. So you need a way to control the reaction, and what they discovered is that you can use plasma for this purpose. In their experiments, they used a spark gap to create plasma, powered with a sinusoidal current with a frequency of 15.3 kHz. You know what else can create plasma with a specific frequency? A Tesla coil. Okay, so I'm suggesting that the sphere is in fact a Tesla coil top load with a fuel cell inside. As long as you have a good enough insulator between the top load and the fuel cell inside it, it shouldn't be a problem to keep them from interfering with each other. The Tesla coil arcs down onto a hydrogen production apparatus, which is, a bit simplified, a tube with a controlled flow of ethanol and water. The arc probably hits an electrode that focuses the plasma arc through this tube. The freshly produced hydrogen then continues directly to the fuel cell inside the Tesla coil. Now, it might seem a bit like I'm trying to cram all the theories into one here by placing the fuel cell inside the Tesla coil, but hear me out. Saving space probably has a pretty high priority with this design, as it already has a significantly lower energy output per occupied land area than the Allied power plant, which produces more energy while occupying only 2/3 the space of the Tesla reactor. Now, this does not necessarily mean that the Tesla reactor is a lesser power plant, it just means that the Soviets care more about the environment. Now you might be thinking, if you have ethanol, why not just burn it? Isn't that more efficient? Well, let's compare. First of all, let's make sure that this design gives us more power out than we need to put in to produce the hydrogen. We're going to use the results from the experiment presented in this article. This method produces 27 mole hydrogen per kilowatt hour, or 7.5 mole per megajoule, and a fuel cell produces roughly 237 kilojoules of electrical energy per mole. So if we divide the output energy with the input energy, we get the energy gain factor. This means that we would get an output power of roughly 1.8 times the input power. So since we get more power out than we put in, this technology can definitely be used in a power plant. Now, to be able to compare it with conventional ethanol combustion, let's figure out how much net energy we get per mole hydrogen. We do that by subtracting the input energy per mole from the output energy per mole. This gives us slightly above 0.1 megajoule per mole. And from this reaction we get 6 hydrogen molecules from 1 ethanol molecule. And the ethanol conversion was 63% at maximum energy efficiency, which has to be accounted for assuming the unconverted ethanol can't be reused. So the net energy output per mole ethanol is 0.4 megajoule. Now let's see what we get from burning ethanol. Complete combustion gives us 1.368 megajoule per mole. Now this is heat energy, which needs to be converted to electrical energy, while the fuel cell produces electrical energy directly. And in ethanol combustion power plants, this conversion typically has around 49% efficiency, which gives us about 0.7 megajoule. So from this data we see that burning ethanol is in fact more efficient. But let's look to the future a bit here. We've been using ethanol combustion to generate power for almost 200 years, and this article presenting hydrogen production using plasma was published just a few months ago, and we are far from the theoretical limit on energy efficiency. So let's see how this technology compares if we manage to maximize the energy efficiency and ethanol conversion. Then we would instead get a net output of over 1.1 megajoule per mole, which is significantly higher than an ethanol combustion power plant, even if you manage to boost the efficiency to 75% using combined heat and power technology. Now the exact energy efficiency of the Tesla reactor we do not know, but now we know its potential.
Soviet technology at its finest.
So in summary, the Tesla reactor is a power plant that quite literally runs on vodka. And not only does it rival traditional combustion power plants in terms of energy efficiency, it produces clean hydrogen, something that hasn't been achieved on a large scale before. And to think the Soviets had this technology in 1972.
Battle control terminated.